Welcome to the presentation 5 of this online algebraic structures course that I'm teaching. The textbook that we are using is Abstract Algebra, Theory and Applications. It's a free online textbook that you can just Google it and find the link. So now let's talk about this structure group. All right. And what we will need for a group is a non-empty set. Okay. So we need a non-empty set. Now, instead of formally defining a group, let me just go through some examples showing you the properties that they satisfy. Okay. And then we will formally define it in a few minutes. Okay. So we need a non-empty set. All right. So let's just take 0 in this set. So now this is a non-empty set. Okay. And 0 is there. And then we would need an operation. So let's take an operation, say addition of real numbers, and this 0 is the same 0 that you have in the set of real numbers. Okay, so this is a subset of the set of real numbers. So here 0 is the same 0 that we take in the set of real numbers. All right. So now what we notice is this, that 0 plus 0 is 0. So we add them together, we stay within the same set. Okay. And if we do 0 minus 0, that is also a 0. All right. So we can subtract 0 from 0 and get a 0. All right. And this operation, addition of numbers, is associative. We shall draw that information just from our knowledge of numbers. Okay, so we have one example here, that is this set 0 is a group. Okay, is a group with respect to addition. Okay, so which properties did it satisfy? It satisfied the properties that if we add any two elements inside this set, we get an element within this set. Okay, and this addition should be associative, which we took for granted. And then we have an identity, that is, if we add 0 to any number, well, if 0 is the only number, we get a 0. All right. And then 0, and then if we subtract 0 from 0, we get the identity. All right. So this is a group. Now let's, for example 2, let's look at, say, here. Let's just look at the same situation. Okay. And instead of 0, let's take 1. Okay, so I'm taking this subset 1. Now notice this, that plus is associative, but if we add 1 with 1, what happens now is that we get a 2. 2 is not in there. Okay, so what you have here is that you may say that this set, which is 1, okay, is not a group with respect to, I'm abbreviating the word, sorry, the sentence, with respect to addition. But notice this, if we change addition to, say, multiplication, then what happens? So then we have same kind of thing happening that we had in the example 1. Why? Because multiplication of numbers is associative, and then we have this, multiply 1 with 1, You get a 1, which is still in the set at the same time, serves as an identity. That is, doesn't change anything else. Okay, and 1 has 1, which when multiplied to 1 gives you the identity that is 1. And whatever I'm mumbling so fast, don't worry, I shall write that all formally in a few minutes. Okay, so this is a group. Okay, again with respect to multiplication of numbers. Now let's just start getting a little interesting here. That is this. Let's take example 4, and in here let's combine -1. Now still you can see that 1 times -1 is -1, -1 times -1 is 1, and 1 times 1 is 1. All of them are in there, and then 1 has, and in fact what you can do is this. I don't know why I'm rushing so much. There is no rush in here. So what we are going to do is we can just, or yes, 1 -1 here, 1 -1 here, and let's write the multiplication of numbers here. So we get a 1 here, we get a -1 here, we get a -1 here, and we get a 1 here, right? So for, every -1 is 1. So when we look at these 4 outputs out of these, they satisfy everything. That is, first of all, product of any two numbers in here is in here, and 1 is identity. 1 multiplied with 1 is 1. -1 multiplied with -1 is -1. So every element has another element that can carry it to the identity. Now, so far, what you did was this, or let's just extend to another example, and then we will take the formal definition. Another means another type of examples. Since we considered matrices in the set of, over the real numbers, and right now we are staying very basic, that is looking at only 2 by 2 matrices. So what I'm going to do is that I'm going to take a 2 by 2 matrix, or rather, I'll just take 2 of them, along the lines of this. I can take even only this one, okay, with respect to product of matrices, and it will be a group. Likewise, even if you did this, that is changed it to these guys, okay, that will also be group. And with respect to what? Multiplication of matrices, okay. I don't think I need that larger font size. I hope this is visible well, okay. Or let me just go to a balance here, okay. So, and this is what? This is a subset of, remember we called M2R as 2 by 2 matrices over the set of real numbers, okay. All right, so real numbers, let me just get our symbol for real numbers from here, okay. So this is a subset, and now here let's call this, just for sake of calling it, let's call it E, and let's call this guy A. All right, yeah, because otherwise making multiplication table would become cumbersome. So now you can see this multiplied with itself will give you the identity, right? And you can verify that multiplied with itself. I didn't multiply. Again, I have no idea why I'm rushing so much. Okay, so that gives you the identity. Or let's go ahead and create our multiplication table. Okay, So we have E, A, E, and A. All right. So EE is A. If you multiply this with this, you'll get an A. EA is A again, and AA is E. So this is in a way exactly like the previous group that we took with 1 and 1. Now just one more example, just to, expand a little. Okay, what we are going to do now is this. So this is 6. Okay, now we may do this, that is, expand this a little by just changing these elements to a little bit more and then examining that, say this is B. Let me reduce the fonts a little. Okay, all right, I didn't reduce it. Okay, here. Okay, so this is, I took a B here, and in B I'm going to change the sign of one of these. Okay, and then C is, what I will do is that I will change the sign here and keep the other one there. Okay, because if we change both the signs, we will get back to E. So this is element C, right? Okay, now you just take your time to verify that, again, if you multiply any of them with themselves, you simply get the identity, and we should make sure that the product of these two lives in here. So if we multiply these, we get A. So here we can again complete the table, and this time we have a lot more, 5. So there we go, and we will write these guys as E, A, B, C, and then again here E, A, B, C. And so when we multiply anything with E, what we will get? We'll get the same set, right? And here we may have to do some work. AE, there is no work. It's, you know, A is A is E, and we found BC is A, but if you multiply A and B, you will get a C. Okay, if you multiply AC, you'll get a B. Okay, and here the associativity is inherited from the associativity of matrix multiplication. Okay, and so this is B times E, and B times A is C, B times B is E, and B times C is A, and then here we have C, B, okay, and CB is A and CA is E. So we have all the properties of group because we have the identity, multiply any two of these, the product ends up in here, and for every element we have an element that when multiplied with that element gives us the identity element. Now before we go further, let's just formally define a group, that when we will call a structure a group, and you might have guessed, we call a structure a group when it just goes through the things that I have been just saying but not writing, right? So finally, let us write a formal definition of group that we shall use for the purpose of this course. And I am going to differ a little bit from the book, okay? But everything else that we would do would be the same. So every property that we cover from the book will follow, okay? So I'm outlining everything that, this should have, where G is a non-empty set and O is an operation. So let's say the book doesn't want, or doesn't need G to be non-empty, but since we are not going that deep into logic, all right, let's treat our groups as non-empty. Sorry, our group as a non-empty set. Okay, and phi is an empty set. Okay, and B, this thing O is what do you call a binary operation? Okay, and what is it? This is just a map from G cross G, the Cartesian product of G with G, to G. And what we have is this, okay, that we define if we take two elements, A, B in G cross G, we will call it AOB. So for example, if G is the set of integers, we can have this operation as addition, and we can go from Z cross Z to Z by, you know, A and B would be A plus B in that case. Or if you take the multiplication, then A, B via multiplication will go to the product. Okay. Then we need this operation to be associative, right? Okay. And we have been talking about associativity, but still let's just formally write it, that it doesn't really matter, you know, which way we combine two elements when we are taking product of three elements here. Okay, the outcome is the same. Those of you who took, say, multivariable calculus, you saw that vector product of vectors is not associative, and and then we require it for all A, B, C, or for all elements A, B, C in group G. Okay. Now it doesn't have to have three elements. Okay. We put three in there. That is, but what we mean is that whenever we take elements A, B, C in group G, we must have that. Okay. So D is that we have, or there is, an element E in G, okay, such that E serves as an identity. Remember, I had been like saying identity in the examples that I was writing before this. So that is an A, and this is A times E. And again, this will be for all A in G. Okay, so for example, say we were taking the integers with respect to addition, 0 is an identity, because if you combine 0 with any other integer via plus, you know, it leaves it unchanged. And here is the last requirement that we are putting in, that is for each A in G. Okay, that is if we take any element in the group in the set G, okay, we have an element A inverse, which could be A itself. All right, so we are not writing another. Okay, so we have A inverse in G such that, okay, such that if we multiply or if we combine, and again, notice this, I'm not using this symbol anymore. That was just to stress that if I take any two elements, then if we combine them via this operation, it should be in G. Okay, so let me come back here such that A combined with A inverse, okay, is how much? E, right? And we are calling it A inverse. And if we have numbers with multiplication and everything is good, then inverse will be reciprocal in that case. But in general, it will not be. So if a structure has these, okay, so let me fix the English here. So let's write a group G is a set with, let's call it binary operation, O, all right. And of course, when I said binary operation, that means this is already included, but let's just be tolerant with those kind of extra statements, okay? So with binary operation, okay, has to satisfy these 5 properties. And later on, you will see that we mostly need these. We will be taking only non-empty elements, sorry, non-empty sets. Okay, so let's take for this particular presentation, let's just stick to examples only. So you can see that the 5 examples that we considered before making this definition, okay, they all satisfy these conditions of the groups that we considered. I think there was one which did not. Okay, so let's just begin afresh. Okay, and let's take something familiar. For instance, let's take the set of natural numbers, which is 1, 2, 3, 4, etc., etc. Okay, where n is what? Let me just list the first few elements. Okay, 1, 2, 3, 4. Okay, so let's consider this example 1. Okay, so in here you can see plus is binary operation. Okay, so plus is a binary operation, right? Okay. So that part is good. That is, if we add any two natural numbers, we still get natural number. And plus is associative, and we are just letting this property be drawn from the fact that the addition of numbers is associative, right? Okay, and n of course was non-empty. That's how we took it. But when we look for this, that there should be an element such that if we add, say, so for instance, if we do this, if we have an element E such that E plus N equals N, where N is in this set of natural numbers, then we know that there is no such E in N, right? So, and E for addition will have to be 0 if we are looking at our regular addition. So, this with our regular addition is not a group, right? So, N is not a, a group, all right? Okay. So let's take example 2 then. Well, it did not satisfy the property for like addition. How about if we took n with the product of numbers? Okay, so here you can see that the that this is if we multiply any two natural numbers, we'll get a natural number, right? Okay, so this is a binary operation. This is associative, again being product of numbers. And then, well, we have a good news here that 1 is in here such that 1 times n equals n times 1, and they are just n. So we have an identity element, right? So 1 is the identity. But notice this. If I take a number, a natural number 2, okay, then what happens is this: cannot find any number x such that 2x is 1 in n. Okay, so no such x is available in n, right? So what happens is this is not a group either, right? Okay, so let's just expand because we had more things. So instead of n, how about this, that we just take the set of integers with respect to addition and see what happens. So let's just take the set of integers here, and the set of integers would be, so it has 0 in there, and then we got, negative of each of the numbers, right? Okay, so this is the set of integers, and we have addition as the binary operation. So you can see that sum of two integers is an integer. Okay, so that is a binary operation, and let's just formally write it. Okay, all right, that is we got, let's go further up. Okay, so, and actually, you know, if you are saying it more formally, you should say this is the binary operation in Z. Okay, that is okay. This is fine because these are numbers. And then we have 0 as identity that we wanted, right? So 0 plus A equals A plus 0 for all A in Z. And you will see soon that we would go ahead and trim these conditions further down. Okay, so for actually we should say for all Z in Z, and then for any A, or so for any A in Z, okay, we know we have negative A in Z, right? Okay, that is, so we have negative A belonging to G, or rather this our Z here. Let's keep the same notation because that will be important. Okay, Z and Z such that one moment, such that A plus negative A, which is the same as A minus A, right, is the same as negative A plus A, and that is the same as the identity. So every element has an inverse. So what happens is that we got that this structure is an abelian group, or just say this is a group. Abelian because, and we will say that formally because this operation is commutative. Okay. Now before we go ahead, let's do this here. that these conditions that we have for, to establish that this structure is a group, let's trim it a little bit, okay? So that is, we said that multiplying the E on the right also gives us A, and then I wrote it opposite here, and so let's see if we can do this. Let's say EA equals A for all A belonging to G, and for each A in G, and for our discussion it'll be easier if I just change it to B. If we have a B such that BA is E, then what will happen is this, that if all these conditions are satisfied, then BA equals E will imply AB equals E as well. And then after that, we should be able to show that AE equals A as well. So that means we don't have to multiply it on both the sides. We can get by lesser conditions, okay? So first thing that we want to show is that our AOB, okay, is going to be E, okay? So we have here AOB. So what we will do is that let's just go ahead and multiply this with E, all right? So just to insert it here, okay. Now, remember this, we have for any element, we have an element in G such that multiplying that to the left, we get E, right? So we must have, okay, so we should be able to find an element C in G, okay, such that CB equals how much? E. So here, since we have an inverse on the left for A, we will have the same thing for B as well. And now what we would do is that we will go ahead and insert that in here, because see, we have BOA as E, and we want to show that AOB equals E as well, right? So we have this, and now what we got is that we are going to insert in place of E, we have this, and now here the associative property will come in handy. All right, so we have this here. Now we got C, and then we can combine B with A. All right, and then we got what at the end? B, right? Now what happens? You have AB equals this quantity. Now who is BA? BA is E, right? All right, so what will happen is our AOB, which we showed as this quantity, all right, and this we already know that this is E, okay, excuse me. So what is going to happen now is that we have C times E times B, okay. Now E is the left identity, so EB will be B. So this is C times B, and we know who is C times B? That C times B is E, right? So AB also becomes E, all right? And now what we want to show is, so we showed, what did we show? That BA is E, okay? That implied already that AB is E as well. Okay. So in this case, we will not be just going from both the sides in all the examples, especially when we have a non-commutative situation, which we will. Now, we have EA equals what? A, right? And we want to show that AE equals A as well, right? Okay, so if we look at this, we have A O A times, okay? And then who is E? E is B times A, right? And what we just showed was that A times B is E, right? So this is what? E times A. So what we showed is AOE is E times A, and which equals how much? A. So what we got is that if we get left identity and left inverse in there, right? The right inverse and right identity, they will follow. All right. Okay. So now what we can do is, just a second, what did I do? AO E, right? So what we did was that in order to prove that a structure is a group, just proving these existences in on one side or the same side is enough. All right. Now let's take up a few more examples. Now let's go with further examples. That is, that Q, the set of rationals with respect to addition will be group because 0 is the additive identity, right? And 0 can be seen as a rational number, and you have seen that, okay? So 0 can be seen as a rational number, so 0 is the identity, and negative of a rational number is again negative. And if we remove 0 from the set of rationals, that is, if we took this as Q minus the 0 element, okay, then that will also become a group. And why? Because 1 is identity, right? So is a group because the multiplication of number is associative, and product of two rational numbers is again rational, and 1 is the identity, okay? And for any non-zero rational number, we have the reciprocal serving as the inverse, okay? And in the similar manner, we can see that the set of real numbers is a group with respect to addition, non-zero real numbers is with respect to multiplication, and similar statements for the set of complex numbers. Okay, now let's just move on to a very interesting example. There is some history to it, so let me take you there. So now, as the last example of this presentation, we are going to take up Quaternions. And if you type this in your Google search, that the letter from William Hamilton to his son, okay, you shall see this letter. I'm just going to show you a little excerpt from that letter of the example that we are going to take up. So Hamilton gave us what is called the group of Quaternions, okay? Actually, my professor used to call it Hamiltonians, all right? So the way this, these symbols that you see, the way an operation in his mind came about, these was this, that is, it'll be interesting to read the letter at your own. That is, he was walking on the bridge with his wife, and when this occurred to him, he just did this, that he just engraved this multiplication by a knife on the bridge. Okay, so let's see the group that we can construct based on this. So let me do this here. Let me erase some portion and just write the group of quaternions here, because I want to keep this original thing here, okay, as it is. I mean, it was not really by Hamilton. You shall see a picture on the bridge. You can just Google it and type the word and look for the images. So here we are going to look for the, or look at the, sorry, group of quaternions. Let's call them, yeah, just let's call them H, because Q we already used for rationals. So we will take I, J, K, and I square is -1, J square is -1, K square is -1. All right. And here what you have is Ij is K, Ji is -K, okay, and Jk is I, Kj is -I, all right, and then Ki is J, and Ik is -J. So as he writes here, Ijk, if you look at this, this becomes K, right? And Kk is -1, right? Okay, so that's how these are all defined. And if we want this to be a group, we need some more first of all, and we are taking it with respect to multiplication, so we will need a 1, all right, and then we are going to write -I, -J, -K. And since we have to have closure, I mean, we brought these in here, I have to have -1 as well. So let's write the steps better, or we can just say like this, just to write it in short. Okay, that is our H equals ±1 ±I ±J ±K. So 1 is identity, and -1 is its own inverse. All right, but the others behave differently. Like for I, the inverse is -I, that is -I square is 1. Same with J and K, that their negatives are their multiplicative inverses with this multiplication by Hamilton. And actually what Hamilton did in this way is that he gave us a multiplication on R4. Like if you write an element of R4 as this, okay, so he gave us a good looking multiplication in R4. We have multiplication in R, we have multiplication of complex numbers in here, and in R4, the multiplication that we have, they are created by these, the Hamiltonians, and with this multiplication structure, you can verify that, I mean, most of that is displayed anyways, that with this Hamiltonian multiplication, this is a group. And of course, the operation in this group is not commutative. You saw that Ij is Ji. No, Ij is -Ji, because Ij is K and Ji is -K. All right. So this is not a commutative group, which we call what? Non-abelian group, right? Okay. So let's stop here for this part of the presentation. what we will do is in the next part, we shall just continue with couple of more examples. We haven't done any sketches, so we want to see some geometric features of the group as well. And also we had developed a relation congruence modulo, which gives us very good examples in the algebraic structures. We'll take up those first and then discuss the properties of the groups in the next part. All right.